Okay, so in this video, what I was hoping to do was maybe go through some of the organic homologous series, a little bit about their properties and a little bit about the reactions that they'd all undergo. So we'll start off with the alkanes up here. Now, I was actually hoping that at home that you could put 4 A4 sheets together like that, you know, and have a sheet this size, because you need something big as this for all of the homologous series to fit on together. So alkanes here, look, how would you identify an alkane? Hydrocarbons, what does that mean? Carbon and hydrogen only, and all single bonds, okay? Now, if you look at the geometry of the carbon here in the alkane molecule that I've drawn, it's tetrahedral. How will you know if the carbon is tetrahedral? 4 single bonds. 1, 2, 3, 4, tetrahedral carbon. Now, if you look at the difference in electronegativity value between carbon and hydrogen, you'll see that it's 0.35. So going with the rules, what type of bond is that? A non-polar bond. So there is no region of positive and negative charges in this alkane molecule. All right, so what does that mean for alkanes? It means that they will not dissolve in a polar solvent like water, because like dissolves like. What would they dissolve in? Something like cyclohexane, which is a non-polar solvent, an organic solvent like cyclohexane. What type of intermolecular forces would you have between one alkane molecule and the next alkane molecule? Van der Waals. Why? Because these molecules are not polar, they're non-polar. What do you know about van der Waals forces? They're weak. And so what do we know about the boiling points of alkanes? They're low. So remember the A3 sheet we did out in 5th year, and try to remember the properties there. Methane is the simplest alkane, and another name for methane is natural gas. So use for that would be fuel. Remember butane and propane and bottled gas, LPG. So those are the uses. Now, the other thing is here, the types of reactions that alkanes undergo. Your only choice is free radical. So free radical substitution mechanism and its evidence, you need to know that. So the only type of reaction that alkanes undergo, substitution, okay? And the only choice you have is chlorine gas, UV light. So chlorine gas, UV light, the minute you identify an alkane, you're thinking chlorine gas and UV light. Now, if you have a reaction between methane and chlorine, you're going to form chloromethane. If it's the ethane and chlorine reaction they ask you to describe, then you're going to form chloroethane. So it depends on which alkane they ask you to describe. But it's UV light, chlorine gas, end of story, okay? Now, moving on over here to the alkenes, you can see I've already drawn ethene here. What's the functional group of an alkene? C double C bond. So the tetrahedral carbons that we had in alkanes, different here now, look, because you can see the presence of a double bond. So alkanes have tetrahedral carbons, alkenes have planar, so they're both planar, those carbons, because of the double bond. They're unsaturated as well. What does unsaturated mean? Means contains double or triple bonds. How would you test for unsaturation there now in the ethene molecule? Well, you'd add either bromine water or acidified KMNO4, stopper and shake, and observe the colour change. So remember, for bromine water, we said that it was kind of orangey yellow and it decolorizes to colourless, and the pink or purple permanganate also decolorizes. So they're the alkenes. Ripening fruit would be the use of ethene. Obviously there again, same difference of electronegativity, so also not polar, would not dissolve in water because water is a polar solvent. Van der Waals between, because it's a non-polar molecule. And so it would have similar boiling points to alkanes. Their boiling points would be quite low, their gases at room temperature, okay? Now, types of reactions that alkenes undergo: addition. So the minute you hear or you identify an alkene, you are straight away thinking addition. And you have to look between the reactant and the product. So spot the difference between the alkene and whatever the product is. So for instance here, if you have ethene and ethane, what's the difference between C2H4 and C2H6? Well, hydrogen, obviously. So you'll write in hydrogen gas, and anytime you're adding hydrogen gas, nickel is the catalyst, okay? If it's a haloalkane, now what's a haloalkane? Halogens, group 7, so chloromethane, chloroethane, maybe bromoethane, bromomethane, something like that. So again, you have to look at the difference between the two. So with the alkene, you might be adding on chlorine gas, you might be adding on bromine, you might be adding on HCl, hydrogen chloride, or you might be adding on HBr, and you'll form something like bromoethane or methane then, okay? So addition, another arrow coming out of an alkene, addition of water will form your alcohols, okay? Or look, special type of addition reactions where alkenes add on or join on to each other, you're forming polymers. So remember your definition of a monomer and a polymer, and I've just drawn 2 repeating units here, look, of your PVC. So chloro ethane would be the monomer, and that joins together then 2 repeating units. And remember to keep your bonds open here at either end to show that it's a polymer. Okay, ionic addition mechanism and evidence. Remember, you need to know that for the alkenes as well. And then alkynes, look, functional group C, triple bond C. Okay, you could also actually, if you wanted to at home, maybe here you could put in the preparation of ethene, you know, with the ethanol and white aluminium oxide. And down here, maybe you could draw in the preparation of ethyne with the calcium dicarbide and water. But anyway, ethyne, geometry of the carbons, look, planar because of the triple bond, unsaturated molecule because of the triple bond. Again, no difference there, or very little difference in electronegativity, so it's a non-polar molecule, not soluble in water as a result, but would be soluble in cyclohexane. And also remember the van der Waals. So van der Waal forces occur between alkanes, alkenes and alkynes, and those van der Waal forces are the reason why alkanes, alkenes, alkynes have low boiling points. Okay? And remember, because they're not polar, then they will not dissolve in a polar solvent like water. Okay, now next to the haloalkanes here, you could maybe bring out a few arrows, you know, and you're also going to say things like that, you know, they're not polar, they'd be saturated molecules now, so non-polar saturated molecules would be used, they're liquid, so they'd be used as solvents for removing oil or grease, something like that you could put in use there. Now down the centre here now, look, we're going to look at the alcohols, the aldehydes and the carboxylic acids. So I've already drawn the functional group of the alcohol, hydroxyl, OH. Now, this is polar. So there is a significant difference in electronegativity value. The oxygen is slightly negative, the hydrogen is slightly positive. This polar bond here is the reason that alcohol molecules can have hydrogen bonding between one alcohol molecule and the next. So if you have 2 ethanol molecules, you can draw hydrogen bonds between. Because remember, look, where can you have hydrogen bonding? Where hydrogen is bonded to oxygen, nitrogen or fluorine. So it's bonded to oxygen here, so you can have hydrogen bonding there. The presence of those hydrogen bonds means that alcohols would have significantly higher boiling points than alkanes, alkenes and alkynes. And remember, we talked about corresponding alkanes, alkenes and alkynes, because what else determines boiling point besides the type of intermolecular force between the molecules? The size of the molecule. So you have to compare ethanol to ethene. You'd compare butanol to butane, you know, corresponding alcohols. So hydrogen bonding here means that alcohols are liquid at room temperature and they have fairly high boiling points, okay? Also, the fact that you've got the OH polar bond here means that alcohols are C1 to C4 anyway are soluble in water because this hydrogen, this OH bond here is polar, which means it can interact with polar molecules like water. But then remember we said that as the CH bit, as the non-polar, if you like, CH bit increases in length, then the solubility of the alcohol will decrease in water. But all alcohols would dissolve in something like cyclohexane. Now, the other thing then is that the alcohols will undergo oxidation. So oxidation is what you're thinking of here. So oxidation of alcohol to aldehyde to carboxylic acid requires sodium dichromate and H+ ions from an acid. Okay. Now it's primary alcohols that are oxidized to aldehydes. Secondary aldehydes get oxidized to ketones. So remember that. And remember, be able to differentiate between primary and secondary alcohols. So primary alcohols, you know, the carbon attached to the OH is attached to just one other carbon directly. With secondary alcohols, the carbon that's attached to the OH is attached to 2 other carbons, and propan-2-ol will be an example of that, okay? So sodium dichromate, H+ ions from the acid. So primary alcohols to aldehydes to carboxylic acids. Now look at the aldehyde functional group here, C double bond O and a H. So these cannot have hydrogen bonding now because you don't have hydrogen bonded to oxygen, you have hydrogen bonded to carbon. It does, however, though, have a polar bond. Here, look, that's a polar bond, C double bond O, which means that these aldehydes can form dipole-dipole forces between each other. So if you have one methanal and the neighbouring methanal, you can have dipole-dipole forces. So dipole-dipole forces are stronger than van der Waals, but weaker than hydrogen bonding. So that would mean aldehydes would have higher boiling points than alkanes, alkenes and alkynes, but lower than alcohols, okay? And also, the first 4 members of the aldehyde family would be soluble in water because of this C double bond O polar bond would be able to interact with the polar solvent or with the polar water molecules, but all of them would be soluble in non-polar solvents, okay? How would you reduce, just before I go on to introduction, look at the functional group of carboxylic acid, C double bond O and an OH. So look, actually, if you had two carboxylic acid molecules neighbouring here. So if I drew something like two ethanoic acid molecules here, you can actually set up dimers, two hydrogen bonds per molecule. Look, because this is slightly negative oxygen, slightly positive carbon, slightly negative oxygen, slightly positive hydrogen. So look, you can have two hydrogen bonds per molecule. So we call those dimers. So actually acids would have the highest boiling points because they can have dimers occurring here between molecules. Remember again, first 3 or 4 members would be soluble in water completely, and after that solubility decreases as the length of the carbon chain increases. Reduction, nickel, catalyst and hydrogen, so going from acid back to aldehyde back to a primary alcohol. Secondary alcohols oxidize to ketones, okay, so look at the functional group of your ketone. Again, this is a polar bond here, look, so they would have similar boiling points to aldehydes because they can have dipole-dipole forces between them. And look, remember, if you're asked to distinguish between an aldehyde and a ketone, these are your 3 tests: acidified KMNO4, Fehling's and ammoniacal silver nitrate, and remember the colour changes. So because aldehydes are oxidized to acids, they will reduce these reagents. Ketones won't. And remember as well, if you're asked to describe this, you'd have to say about warming or making sure that they're in warm water. Okay, finally on alcohols then, look at the reaction between sodium and ethanol, forming sodium methoxide and water. And remember that sodium floats on ethanol, whereas sodium sodium sinks in ethanol, doesn't it? So it sinks down in ethanol, sodium floated on water when you saw that done in second year. Okay, and again, on the carboxylic acids here, remember you need the reactions between sodium carbonate and water. Now finally, the last homologous series are the esters. The functional groups of esters, look, C, double bond O, and you have the oxygen bridge. Remember the oxygen bridge linking the acid portion of the molecule to the alcohol portion of the molecule. What you need to make esters, you need an alcohol and an acid. So you can see acid and alcohol forms an ester, esterification. The opposite of esterification, hydrolysis. Okay, so the ester reacts with the water and you get back the acid and the alcohol. So an ester reacting with water, hydro. Hydro implies the ester is split when it reacts with water. And finally then, if you have base hydrolysis of the ester, then you form soap. And you could even put in a little bit of detail here maybe perhaps about the saponification or making soap or base hydrolysis of esters. Okay, thank you. Hope that helps.